We're going to be also looking at this talk a little bit more on adaptive experimental design in these sort of hybrid models settings. Our speaker, Dan Russo, is a professor at Columbia Business School. He got his PhD at Stanford and did a short stint at as a professor at Northwestern before going to Columbia. Looking forward to his talk.
Thanks, Ken. Okay. So yeah, I'm Dan Russo. What I'll talk about today is joint work with Chao Chin. And we're going to be thinking about multi-arm bandit experiments. And in particular, we'll be thinking about this kind of fundamental tension between adaptivity, really the key design principle that one usually thinks about in bandits, and a tension where they risk confounding in settings where there's non-stationarity during the time period of the experiment. Okay, so for most of my career, I've been interested in all these problems that involve interactive learning. And for most people who work in this area, I think this is kind of a timeless field, but it's spurred on by this explosion of interactive data sources in the real world. Now, a key paradigm for this class of problems is the multi-arm bandit problem. I'll show you here a little video from Stitch Fix, who employ the Thompson sampling algorithm, which we'll be building on today. In that setup, there's a bunch of different arms, A through F. The agent here, this octopus-like thing, is beginning with prior beliefs about the quality of each of the arms. And then it's going to go sequentially pulling the arms and trying to figure out which one to deploy in the future. Okay. Really rely on companies to create better videos than us. I like this. So, and one thing, if you really go back and look at how it plays here, one key feature is that when it figures out an arm is really bad, it discards that, right? Once it learns it's bad, which could take very few samples, it doesn't keep playing that arm. Really, most of the samples are gathered from the good arms. The basic idea there that adaptivity could offer greater efficiency, that's kind of the key idea in this field. And classical theory crystallizes this. Going back to Lai and Robbins, crystallizes that benefit in problems with small decision spaces. But as you look toward more complex problems, it's often really crucial that you deploy some adaptivity in your information collection. Right? As you learn in a decision problem about which actions are good, you zero in on the competitive part of the decision space and discard the rest. And you can kind of convince yourself this in different ways. In this shortest path problem, there's an exponential number of paths. You just can't try them all. You need some smarter way to search. If you think about convex optimization, the kinds of algorithms we use there, they pretty quickly zero in on a part of the space, discarding the rest with a few measurements. So the theory in this field really emphasizes this aspect of the design principle. Now, there are lots of documented industry applications of bandit algorithms. They're in use in different companies. The academic literature has picked this up, and you see specialized models in all sorts of disparate areas, things I don't even have up here, drug design and so on. But if you're a person who works on this field, it's worth kind of being a bit humble and taking a step back and realizing that despite all the promise of this efficient adaptivity, classical randomized control trials are really still the gold standard in most areas. So we seem to be missing something. And I don't think it's just kind of the engineering effort to deploy the algorithms. So here is a description from the Lift Tech blog. It says the outside world often has a much larger effect on metrics than product changes do. Users can behave very differently depending on the day of the week, the time of the year, the weather, and whether they learned about the website through an online ad or found the site organically. Controlled experiments isolate the impact of product change while controlling for the aforementioned factors. That's how they're thinking about what's important about running experiments. So a special case of our model, it's actually an easy special case of our model in some sense, is going to generate plots and scenarios like what I've shown on the bottom here. And in problems like this, there's a kind of a core tension between efficiency through adaptivity, where what you want to do is use early measurements to quickly zero in on the most effective part of the decision space. If you tilt your head a bit, you can see that this kind of adaptivity is really saying you want there to be a pattern across time in how you select actions, right? You mostly want to select the bad actions at the beginning and not much later on. So there's a tension where when there's a pattern to how you select actions across time, you can risk confounding. So here, if you mostly played arm 3 at the beginning and you mostly played arm 1 kind of here in the middle, you may mistakenly think that arm 3 looks better than arm 1, just due to when you played it. So what I want to do in this work is, well, there's going to be a modeling component, an algorithm component, and a theory component. And in terms of modeling, I want to write down a model that can generate plots like that and richer ones, and generally take seriously some of the concerns underlying classic randomized control trials, take seriously the motivation of that lift tech block. And you'll see kind of a new twist on a model of Bandit experiments with many of the same elements, but if you look at it carefully, doing well in certain hard instances is going to require robustness to delay, robustness to non-stationary confounding factors. In terms of algorithms, we don't want to start from scratch. Instead, we're going to take the Thompson sampling algorithm that Stitch Fix was using and see whether we can just carefully tweak it. So we're going to come up with a sort of careful but pretty simple way to tweak these algorithms to make them more robust to certain model factors. And then finally, where a lot of our time was spent is in this theory component, we're going to have two sorts of results. One that generates very hard instances and stress tests whether we still get good regret bounds of a certain kind in those settings, and one that asks, in the other extreme, if you had a more benign stationary environment, do we get these kind of like Lie Robbins style efficiency through adaptivity sort of results? Now, the nature of a talk like this is that you kind of need to do the first part to do the second, and you kind of need the second part to do the third. So I will probably run out of time and not do sufficient depth on the third part. It's an unfortunate factor of studying a new model. So I'll give you sort of some teasers up front. So if you're someone who's interested mostly in the third part, there are a few things that I think are interesting here. One is we're going to see some results about the importance of randomization. So maybe the two most common design principles for multi-arm bandit problems are Thompson sampling and UCB. And if you asked me many years ago, I would have thought that they're mostly working the same, right? They work well in about the same settings and work poorly in about the same settings. In our setting, though, we're going to see a provable gap. So problems where UCB really, really fails, and yet Thompson sampling works pretty robustly. And I think that the key is randomization. A second kind of interesting nugget is we're going to use contexts like the time of day or something in the lift example, just to deconfound our inferences. And in our results, the price of doing that is going to be very, very small. Okay. So if you're used to contextual banded bounds or something, they say that you should be very judicious how rich you make your features. That is not going to happen here. And the last bit is our policies are going to be, we call context independent, meaning in a certain setting, we're going to take actions after seeing the context, and there's actually going to turn out to be no price to them. All right. So with a intro that's that broad, you kind of can't give, hard to give a related work discussion. It's sort of whole textbooks that are related work to something like that. But I guess I'll really call out that I think that the closest intellectual line of work is going to be work on non-stochastic bandits and non-stochastic best arm identification problems that lets there be very adversarial patterns to arm rewards across time, and some that try to find like a best of both worlds. Any questions on the broad warm-up? All right. So to set us up, I think it's worth just looking at one kind of prototypical example of an experiment at a tech company. So here, this is to set us up with kind of what we want to model. So here we have the Spotify app. And a few years ago, they rolled out a new feature, which is this shortcuts page at the top, which helps you return to whatever's heaviest in your rotation at that moment. Whenever some product change like this is done, they run an experiment. So what's the goal? The goal is to test out a few variations about what they productionize. Do we want 4 buttons or 6 or 8? And should we productionize model variant A, which maybe is trained on a certain notion of short-term proxy, model variant B, which uses a different architecture, but the same short-term proxy of success, model variant C, which maybe uses a different proxy. And the reward measures are actually these kind of like more holistic things, like do people use the app more, or do they complete search? Do they have to go to search less often if they have this? So in the realm of models, I can kind of break down the space of things that people in this literature study into 2 dimensions. And the experiment that I just described really sits on the top right. It sits on the top right in that, well, one thing, their objective in the problem is to reach a standardized decision. They are not going to productionize one algorithm for me and a different algorithm for Kevin. They're not going to design one algorithm, one UI that I get in the morning and one UI that I get in the evening. They make one decision, and that's what they launch. The other sort of measure here is they are mostly going to be focused on reaching a decision that then gets deployed and hoping that that works well kind of going forward in the population, and are a little less concerned about the reward earned during the process of running the experiment.
So regarding the first distinction between standardized decision and personalized decision rules, couldn't the standardized decision rule be personalized?
Yeah. I think what's funny here is that the shortcuts themselves are personalized, right? The algorithm that they're productionizing is a personalized algorithm. This is like a meta decision of which personalized engineering algorithm that I deploy, which deep neural network do I deploy?
Let me rephrase, like in that terms, like are you saying that the action set is small, or like what are like something like that?
Let's hold that for a second.
Okay.
I think what I'm saying is the action set's an action and not a policy.
Yeah. Okay.
So give me one,
Okay.
2 slides.
Yeah.
Okay. because I want to first talk about the left to right axis here. Okay. Now, I think what's important about what I'll describe, so we're going to describe a model that is also in the top right corner. Intellectually, I don't think it's important that you're in the extreme of the top right corner, but I think it is important that you have elements of that. So you could be kind of in the middle, but going to the boundary in either other direction may change things. So sort of separate from this paper, we have thought in different cases about how to interpolate between the extremes. So here's a model that goes between an objective where you want to stop the experiment and make a good decision for the population, and a model where you want to have high reward while running the experiment. You can kind of come up with a nice weighting factor where you balance the two objectives and think what's the right policy to deploy in each case. A natural one to deploy is this thing I'm going to call top 2 Thompson sampling. It's an older algorithm I once proposed. It has a tuning parameter in it, and that tuning parameter can be set based on how strongly you want to target one of the two objectives. And you could also interpolate the other way. So what I would call complete standardization, to Chaba's comment here, is one where you want to reach a single decision that is invariant to the context. I don't want a different UI for each time of day. I don't want a different UI to each for each different market. Now you could move toward complete personalization, which is where for anything I could measure about you, I base my decision on that. I'm going to change the UI based on what you clicked on last. This is what I would think of as complete personalization. And you could go in between, having different UIs for different markets, but not changing it based on what you clicked on last. And those sorts of rules, I would say, involve restricting the policy class. So what I think is important about this model is that we're not going to be all the way to the right.
Yeah. Can you say a little bit more about what the dependencies will be then? Will it effectively be the size of your context space that you're doing the conditioning on, or the policy class? What will the direct guarantees depend on for that middle ground between those two?
Great. So in some case of with non-stationarity, I only know how to analyze the far left. If you assume things are IAD, you can get results that depend on the richness of the policy class through an entropy term, roughly through the log number of policies. So sort of, if you went to the far left, you really only depend on the log of the number of actions. It's quite nice. If you went to the far right, you start to depend on So I'll just say 2 more cents about this. This is, I think, if you're coming from a contextual bandit background, suggesting, yeah.
With respect to best in class, then is that
It's a best in class.
Best in class.
Yeah, thanks. So I'll just say 2 more cents on this before I move on. If you're curious about this, there's a whole discussion in the paper of this tension between standardization and personalization. Because I think if you come from a contextual bandit background, it's kind of obvious that, well, what I want to do is maximize reward in each instant, independently of the rest. What's sort of happening there, though, is you're assuming that your decisions at different points in time have nothing to do with each other. Now, often, if you really think how these techniques are deployed, it might be that the user opens the app, and then 3 minutes later, they come back to the homepage. So there's a natural coupling between the two. If you were to change the UI every 3 minutes on them, they would not like it. So that is what I'll call a consistency benefit to deploying one version. There's also an operational benefit. No one would want to maintain different machine learning algorithms, like hundreds of them. If you go to the McDonald's example, there's, again, a consistency benefit to having every store be the same. It's part of the business offer. And there's an operational benefit too to running their supply chain that way. So the paper has a bunch of different discussions around these and why they show up in different examples. I think it's interesting to think through, but probably not where I want to spend most of the talk. So you can just think we're living a little more to the left. Where are we? So I'm going to write down a model like this. We are going to take that product testing example and observe that passively, when you run the experiment, you don't just see how the user who got this treatment responds. You see a bunch of other contextual information. You see details of who that user was. You see the time of day when they came to the app. You see whether there's a promo running that sits maybe above the shortcuts and messes with the experience. You see whether they were interacting via voice commands and so on. Okay. Now, the contextual information is maybe useful because it's going to help us control for these risk of confounding and so on. But it's not something that you need to run an experiment to learn about. Right? So users who were not in the experiment, you still see their contexts. And you can often just look at past data to figure out, okay, what is the age distribution of my users? We're going to be assuming that basically the company really understands contexts. They just don't understand whether 4 buttons or 6 is better. So that leads to the following model, which is a contextual version of the best arm identification problem. The objective in running the experiment is to learn which arm to deploy throughout a population, and you will be deploying that arm across all future contexts. So with perfect knowledge, we would make a utilitarian choice, which maximizes the average treatment effect. And that's therefore maximizing the average, weighing across how often contexts are observed in the population, the performance of this arm in this context, which, making kind of a canonical assumption, I'm going to assume it can be expressed through the inner product of a known feature vector associated with the context and an unknown parameter vector associated with the arm. So there's 2 forms of prior knowledge represented here. One is I'm assuming that this distribution over context is known. So we discussed that before. The other way we're going to represent prior knowledge is I'm going to assume that these theta parameters are drawn from some prior distribution. It might be that based on past data, if you're doing a pricing experiment, you understand that certain customer segments are price sensitive and some are not. And you'd like to bring that to bear when you run this new experiment. You don't want to start from scratch. Okay. So there's 2 more parts of the model that I'll wrap up here. One on the left is how do we gather information? And on the right is how do we use information? So we're going to gather information like this. We're going to run across rounds. In each round, we're going to see a context. We're going to pick a treatment arm to employ, and then we're going to observe a reward associated with playing that arm in that context. Now, maybe not something you need to focus on in this talk, but the model in the paper actually also allows for delay in seeing that reward, but even very long delays in seeing the reward. Okay. Now, how do you use this information that you gather? Well, at the end of the experiment, we're going to have a history, which summarizes everything that happened across capital rounds. The price of unresolved uncertainty at the end of the experiment can be expressed through what Stefan Wager has called the utilitarian regret. I like that term. It is comparing the difference in utility across the population if you were to employ the true best arm in the population and the best you can do given your imperfect information represented.
So who decides what T is? Because it seems like in best arm identification, the platform will decide what T is. So in this,
so we're gonna have two kinds of results. Unfortunately, there's some ambiguity because both models exist. One model is where T is fixed, and you just try to understand how you do for fixed T. And another way of studying things allows you to stop adaptively. For one part of the paper, it's much cleaner to have T be fixed. And something that's a real headache is that asymptotic results are not understood in the literature if T is fixed, even if it grows. And so in that case, we're going to let the algorithm adaptively stop. The most other parts stay the same across the T settings.
I have two questions. So the first question is, so you talked about confounders at the beginning of the talk. So is the context essentially, is this how you model a confounder?
Okay. Yes. So here's what's sort of a subtlety here. So we're going to see how actually many things like that non-stationary picture I showed you at the beginning are actually a special case of this if you give yourself enough flexibility in how you represent the context. Like the context could be an indicator of the time period. So I'll show you that. And really what's going to be surprising to me here is whether you make those contexts IID or let them be kind of follow any weird pattern is going to change the hardness of this problem quite a lot. You had a second question, right?
So like post-experiment, you can only pick one arm, but then in the adaptive, you can change the arm that you pull at every time step, right?
That's right. Okay. That's right. And how adaptive you can be is restricted maybe only through this. All right. So I said we're gonna make sort of a small tweak to a canonical algorithm, Thompson sampling algorithm. And maybe the interesting thing is that this tweak is enough. So it's really two tweaks. The one that's really new to this work is we're gonna change the learning part. So usual Thompson sampling, there's kind of two versions of how you might think about it. One would just act like the world is IID and try to play an arm according to the posterior probability that it's the best arm at each time step, right? So it randomly samples an arm according to the chance it's the best. That version of the algorithm, though, would be clearly at risk for confounding because it's acting like the world is IID, ignoring contexts altogether. There's a second version, the usual contextual bandit version, that aims for full personalization. It plays an arm according to the probability that it's the best one in this given instant, or given what you clicked on last. Now, because we are after what is the best arm to deploy in the population, we are going to incorporate all the information we have, including the context in the past, and form beliefs about the posterior probability that an arm is the best to deploy in the population. That's what I star is here. And we sample an arm according to that probability. Now, there are kind of nice algorithmic ways to do this, especially with Gaussians, because linears and Gaussians play really nice. So the subtlety here is really, why does this work? I'll tell you if there's time that if you do deconfounded UCD, it does not work. I'm mostly going to skip the second piece here because it's kind of from an older paper of mine. But that's saying if you wanted to optimize not for regret in the experiment, but you want to make sure that with a small number of measurements, you're confident about what to deploy in the population, you tweak Thompson sampling a little bit. So kind of to Jackie's question, here's where I think this gets interesting. What I wrote down looks a lot like a canonical linear contextual bandit problem. So it's surprising that there's something new here. And that becomes a little more clear once you start writing down specific examples. So here's the example that generates these plots I showed you at the beginning. In this case, I'm going to take the context vectors to be standard basis vectors. Basically, they're an indicator of what time period you're in. Now, the ideal choice in this experiment is going to be the one with the highest dashed line, representing the arm with the highest time average across the length of reward across the length of the experiment. And you could write that as a special case of our model by taking the W to be a uniform across the time periods. Now, the plots below use a particular model for how the time-specific performance of each arm varies across time. It says that there's a fixed arm effect. Some arms are just better than others. And then there's a additive and shared time effect that leads to maybe just overall higher rewards or lower rewards at different points in time. This is actually not such a hard special case, because you could sample two arms very close together and take the difference in their rewards to form a nearly unbiased estimate of the difference in their true qualities. And the tension is, what does very close together in time mean? By choosing this kind of bandwidth parameter in this Gaussian process prior, we could generate a case where things move very slowly. So you could compare arms that were measured far apart from each other in time. You could generate cases where things move very quickly. And you need to really measure close in time to have comparisons across arms. Now, the Lyft Tech blog mentioned lots of variables in words that they could measure that are sources of possible confounding, time of day and all sorts of other stuff, features of the users and so on. So you could take this model and easily tweak it by adding a shared observed effect here, which controls for observed confounders. Still, actually, this is not the hard case. The hard case is going to be when we let things cross. Okay, we're going to let arms be much better than others, maybe at the beginning, and then worse later on. And that comes in when we add a third term here, I guess a fourth term, which is time and arm specific shocks. And really, if you're being Bayesian here, you can control how hard you think this problem might be by understanding, do we put a high prior covariance on this, letting like really weird things happen? Or do you put a small prior covariance on this, saying that pretty much arms that were bad in the beginning and much worse than other arms are unlikely to overtake the others?
We're not going to allow feedback cycles. It can't be that if you pull one arm a lot at the beginning, it makes that arm worse because people get tired of it.
Great, great. Yeah, I'm not getting to that. I think that's really where you get into RL. Yeah, we're not going to allow feedback cycles where the fact that I've like invested in an arm makes it good, or the fact that I've invested in an arm makes people bored of it. So, okay. All right. So to put words to this, I mean, it's always helpful to know what's the example that breaks people's theory. You don't want to say, okay, what breaks UCD or something in these examples? It's this. This is what really breaks things. And I'll give it kind of a story. The story is that you're running a week-long experiment, trying to figure out how to set a price for an iPad. Right, so your Apple pricing iPads. For that to happen, you are trying to run an experiment for 1 week long and you want to pick a price. You don't want to have cheap iPads on Saturdays, because in the future, people would just only shop on Saturdays. Nevertheless, there are day of week effects where the people who shop on particular days might have different willingnesses to pay. And therefore, you need to control for day of week when you run the experiment. Now, here, the key feature to this example is that the contexts have the following setup. The first 1/7 of contexts are Monday. So your contexts go Monday, 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 then Tuesday, 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 Tuesday. Finally, at the end, Sunday, 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 and then it's over. You never see Monday again. It's a 1-week experiment. So there's really two challenges here. One that's maybe more intuitive at the beginning is day of week effects will confound your inferences if you don't model them. The second one was surprising to me at first, is a way in which nonstationarity is almost intellectually the same as delay. Here's the issue. If you were to model day of week effects, saying there could be something special about Sundays, you actually don't see Sundays until the end of the experiment. So somehow it takes the whole experiment to learn everything that you could learn, no matter how many users show up per day. And if you really try to think about it at just some abstracted level, information delays like this are the enemy of adaptivity. Because adaptivity is about learning in the beginning and using it to adjust your treatment decisions. So if you can only learn at the end, you're in trouble. It's going to be very. So we are here. In the paper, we go through very formally and show that, well, first, if you just pretend there are no day of week effects, you can get into a lot of trouble. No matter how many people show up, you might pick the wrong arm to deploy in the population. More surprising, I think, is if you take the deconfounded UCB analog of our deconfounded TS algorithm, it actually also fails. And it fails because, roughly, go through this carefully, what optimistic algorithms like UCB are trying to do is they are designed based on the idea that if they think an arm is really good and they try it, they'll quickly, and if they're wrong, then they will quickly resolve their uncertainty. Their confidence bounds will go down. But if you think an arm might be really good throughout the week, but you haven't seen Sunday yet, trying it on Monday just doesn't resolve your uncertainty. You just have to wait. And so these algorithms, what happens in the counterexamples is UCB just plays the same arm for like all of Monday, and it just didn't gather the information on Monday that it needed about other arms. Oh, all right. Told you I would run out of time. So the much of the work then was once you go through this modeling and development of an algorithm and so on, is trying to crystallize a sense in which, well, the tweak we've made to Thompson sampling is going to allow it to actually work robustly in some of these cases where there is all this nonstationarity. Now, in some ways, that part is about saying that if the problems are really hard and all you could do is run a randomized control trial, Thompson sampling will, in some sense, do as well as that. So the result on the left is a kind of robustness result. It can really be understood as saying that for really hard instances, like the day of week problem, kind of all you could do is wait till Sunday. The algorithm does not get screwed up. And in those settings, it's going to get roughly the same bound as a non-adaptive like RCT style. Over here, we're going to extend the machinery around studying the asymptotics of best arm identification problems to settings with contexts, where contexts give you additional information and so on. And there, if the contexts are IID, we can really formalize that this TS algorithm is essentially asymptotically optimal up to second order terms. So this is like a Lie-Robbins style optimality result. And the trick here is probably not to get one of these results. It's really the hard thing is coming up with a natural algorithm that might work well in between the two cases, but gets both. Sort of stress testing different things. If you want to do as well as an RCT, the easiest thing to do is to run an RCT. Right? And what that would do is not adapt at all. Whatever you see in the beginning of the experiment, you don't respond to it, and you're very robust. The way you get the result on the second is you adapt as aggressively as you possibly could. As soon as you learn something's bad, you allocate more measurement effort away. So it's kind of delicate to see whether you can kind of get both. I think that I will close here and instead save some time for questions. Just for the connoisseurs, sort of say that if you wanted to like learn new math about bandits, this first one is the robustness result seems to have new ideas because it's trying to analyze Thompson sampling style algorithms using inverse propensity weights to analyze the posterior. All right, I'll close here. Thanks.
Questions?
Thanks for the nice talk. I think I didn't quite understood the adjustment to the Thompson sampling. I was wondering if you could use your nice example of Monday to Sunday to tell us like.
What's it doing?
Yes, exactly.
Yeah, so here's what the algorithm will do. I have beliefs about the magnitude of all these effects, the arm effect, the day effect, the interaction effect. Right? So I have prior beliefs that allow me to form a posterior based on what I've seen up to Tuesday. And then those beliefs might tell you that interaction effects are small, and that whatever performed well on Monday and Tuesday is likely to perform well going forward. Or it could tell you that Sundays are really different and arms could overtake each other. Anyway, so as I've gotten enough data, I form a posterior about what might be true of the future days. And based on those beliefs, I ask, what's the chance that arm one is the best? Not so far, but throughout the entire week. What's the chance arm two is the best? Not so far, but across the entire week. Arm three, and so on. And then I play arms according to those probabilities. Usual TS would have, well, different instantiations. One just pretends there are no day of week effects. It's kind of just wrong there. The other is on Tuesday, I'm going to play an arm according to the chance it's best on Tuesdays. But if I really want to set a price for the week, price across future weeks as this Apple pricing tablets, that also is kind of the wrong way.
So I need to know kind of information about that interaction effect, right? I was just wondering how sensitive it is. Like knowing that may also be kind of.
I think that, so my rough understanding is that if you believe that interaction effect can be completely arbitrary, can be huge, can change a lot across days and so on, you're really almost in an adversarial. Very weird patterns can happen where arms are one arm is just clearly the winner, and the other top arm just overtakes it completely, even though it was bad on all other days. You really would need, my rough way of thinking about this is if you were pricing many different products regularly, you would need to look at past data and try to calibrate basically how weird are things.
So, I mean, I see like UCB is a bad algorithm here, but Lin UCB seems the right comparator because there you sort of find the context within confidence ball, but then you want to not be optimistic for the current context with population. Is that the right?
That is deconfounded UCB. What you're describing is what I'm calling deconfounded UCB. It forms beliefs correctly, forms uncertainty estimates correctly, but then plays optimistically, and it actually doesn't work. Yeah.
So the establishes variation between UCB and Thompson sampling. We probably need some axioms of what UCB, like the confounded UCB is one particular example of how the UCB principle could apply. So is there separation more general, or is it because like I could imagine, for example, that you classify something as UCB as having some amount of response that the mean is below always, and yeah, like, I guess to what extent the separation is about this particular association with UCB compared.
I don't know exactly how to form the axioms, but I do think they exist a bit. It's really the idea that you could be in a situation where on Monday you learn nothing. And if you respond to that by playing whichever arm you're most optimistic about, in some sense, you're going to be playing one-off because your optimism is not really changing. You really have to wait till Sunday. And so there's something about being deterministic in the face of uncertainty that deterministic and kind of like optimistic like that in the face of uncertainty that breaks things. It's a good question how to axiom it so it doesn't look like this particular algorithm. I don't break.
Yeah, let's leave it there. Answer questions during lunch. So feel free to go. Back to you. Yeah, I know.